Welcome to Session 4 of Clocks and Registers. The first exercise has us determining the operation of a simple circuit based around a set-reset latch. We begin by recognizing that the set and reset inputs to the latch are only valid when the enable input is high. So these are the only sections of the input waveform that we need to look at. Taking the first one, we see that the inputs to the AND gate are satisfied, and so the latch is set. With the next active enable input, the high in A signal both disables the AND gate and activates the OR, so the latch is reset. The low in B signal of the next enabled period again disables the AND gate and asserts the OR, again resetting the latch, which changes nothing. The conditions of the last enable time are the same as that of the previous first one, setting the latch to complete the waveform. We add muxes to the mix in the next exercise. Again, we look only at those clock periods when the enable is asserted. For the first enable time, the low mux select means that the A mux inputs get passed along to the latch. And since the latch set input is low and the reset input is high, the output remains low. Moving on to the next enabled clock period, we see that the mux select is still low, but now the latch inputs are reversed. Now it's the set that's active. And so the latch output goes high. The mux select now goes high, allowing the B inputs through. And although the inputs in 1 and in 2 have reversed states, we're still setting the latch. So no change. On to the next enabled clock period, and the mux select is still high. And in fact, we find that the two inputs are also the same states as the previous time. So again, no change in the latch output. For the final enabled clock period, the mux select now goes low, and the high in 2 finally resets the latch. With the last exercise, we get some practice managing the clock delays associated with registers. As we know, only those clock cycles with the enable asserted are meaningful to the enabled data registers, but we begin by noting that we don't know what's happening at the beginning of the first register, DAT D1. We do know, however, that the input values of DAT are transferred to DAT D1 during the active enable periods. And the value of 1 is held until the next enable time, along with 4. We move on to the second enabled data register, DAT D2. And first we'll see what's up with its enable input, N D1. And of course it's simply a delayed version of the input enable, giving us a delayed version of DAT D1 for the final output, DAT D2. And we see an important point illustrated here. By delaying the enable through the D flop, we're keeping the original enable signal in sync with the data flowing through. With this session, we'll be exploring how the latching and holding feature of registers can be used for data storage. We begin with 4 enabled D flip-flops latching a 4-bit vector value. And we'll condense the 4 flops into one symbol, remembering that the symbol represents 4 separate registers. Next, we duplicate this 4-register set 4 times. Take note that we now have 16 D flops. Note also that each set of 4 flops has its own enable input. Instead of tying the enables together as we have been doing, we're going to control each one separately, which means that each of the 4 word vector registers will latch the DIN input individually, and we begin by using an AND gate on the first register's enable. By including inversions on the AND gate input, its output goes active only when both inputs are low. Thus, the register's enable is made active by a decode of 0. By adjusting the states that activate the AND gate, we can create other decodes like 1, or 2, or 3. Note that at this point we've gone through all the possible combinations of a 2-input AND gate. And now we take a big next step. We use a different decode value for each vector register and introduce a new 2-bit vector input signal that we'll call the address, or ADR for short. We can see that the first register is enabled when the address input is binary 0. And we'll label the output of that register DS0 for data stored as addressed by 0. The third one is enabled when the address is 2, and so on. With a 2-bit address, we can individually enable 4 registers, all the combinations of 2 binary bits. So now the address input controls which register latches the data, but we'd like a little more control over when the data is latched or stored. For that, we add another input signal that gates or enables the address decodes to latch input data. And we'll call this new signal write. You can probably see where this is going. Given these inputs for data and address, if the write signal looks like this, then the register outputs will be this. Next, we add a multiplexer, a mux, at the output side of the registers. If a binary 0 is applied to the mux, we select the value stored in the first register. And when, for example, a binary 2 is applied, we select the third register. We can add an output signal, dout. But what do we do about the mux selection? We'll add another address input for the mux selection, and we'll call it the read address, RD address for short. We're done with the right side, so we'll get rid of those waveforms to make room, slide the register values up, and add a sample sequence of our new read address to the waveforms. When the read address is 0, we're selecting the DS0 register for the output, Dout. During the first part, we don't know what the value in the register is, but during the second half, we know that the output will be hex A that we wrote into the 0 register earlier. Similarly, the output is hex B from the second register, followed by D and then C. Note that we've selected, i.e. read, values from the registers out of order. We can obviously read from the registers in any order we wish. Here we'll pause a moment. In this example, we have 4 vector registers, the ability to latch and store 4 4-bit words. But as we'll soon see, in practical applications, there could be many, many more registers, and thus many more register outputs to mux together. This is not a problem at lower speeds, but at normal operating clock rates, this becomes increasingly difficult, since inside integrated circuits, it takes a tiny but finite amount of time per signals to get around, and with so many traces, a signal might not make it to the next clock edge in time. Therefore, we add a register at the mux output. There's still a race for the storage register output signals to get to this register in time, but at least they have a fresh start to get to wherever they need to go after this. Adding a register stage for timing purposes is a very common thing in real-world designs. There's a consequence, though. The final output is now delayed another clock time. Here, the 0B value selected by the 01 read address appears out 1 clock later. The same thing with 0D selected by 11. We're now going to take an important step. We'll collect all the logic into one component where I'll rename the writing address for consistency. You can see that we've created a memory. And remembering that we can read in any order we wish, we can call this a random access memory, or RAM for short. And as we know, RAMs can be billions of addresses deep. That's a lot of signals to mux together towards that final output register.